Good morning to all of you. Myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi. So I hope my screen is visible to all of you. So thank you for joining this session. In this hands-on, I will show you a very innovative simulation tool for a multi-scale DFT and DFPT solver, that is RESCU. And first, I gonna show you some presentation about this company overview on this software. And after that, I will start you live. So basically, this Impulse technology is based in Gurgaon, which provide nanoscale device and material simulation software, up to latent device simulation software, and cloud-based material simulation software. And my most valuable partner, that is Nano Academy Technology. So basically, this Impulse technology is a distributor of this Nano Academy Technology software. So this company is basically a Canadian-based company who provide a nanoscale simulation tool where you can simulate the crystal structure, molecule structure, device structure, graphene, nano ribbons, nanotubes. And apart from this, if you want to work on optoelectronics domain like perovskite, tandem, organic solar cell, thin film, OLED, then we have another partner. And suppose if you have some problem in your cluster, like some SPG server is there, so that is not good for DFT calculation, then we can also provide you the cloud-based material simulation software where you can run the simulation on Amazon and Google server, and you can download a result through online cloud resource. So these are three major partners that we are presenting in India. So today we have scheduled this hands-on on this Nano Academy technology and its product. So I will focus on this Nano Academy technology. So this company was founded in 2008 by Professor Hungo, Dr. Zhu, and Dr. Lee from McGill University. It was developed for molecular quantum transport software. Initially, they developed the nanodical software, which is dedicated to quantum electronic transport modeling. And after that, they developed the RESCU software. And the goal and objective of this tool are for enhancing the material development. And we have several unique features and more development are released day by day. So basically, they are located in Montreal, Quebec, Canada, originally from McGill University. So if we talk about the journey of this software, so basically in 2001 from McGill University, where Professor Taylor and Professor Ungu, who developed the quantum transport package first, which is also supported by some Northwestern University in 2002. And in 2008, they lead this foundation of this Nano Academy technology. And officially, this Nano Academy technology was released commercially in 2009. In 2009, they developed the nanodical software, which is dedicated to quantum electronic transport calculation. And in 2015, they developed the RESCU software that is address the large-scale atomistic simulation for material simulation, which is based on a set of art DFT and DFPT solver. So apart from this background calculation engine, here you can see the user interface is there. And this interface will help you to model the structure. You can build your simpler structure, complex structure, and you can do the simulation. And even recently they have launched this RESCU Plus. So if you want to work on advanced level, so this RESCU Plus will be helpful. So this is a general overview of our tools, basically both RESCU and Nanodical, which are two main brand of material simulation tool. They include a broad range of advanced method for simulating complex material property at different levels. Also, they have tool and toolbox that can used for effectively preparing the calculation, executing the calculation, enlarging the result that comes out from the atomistic simulation. Now the advanced tools are there for building the structure. You can build a crystal structure, molecule structure, device structure, and manipulate this property. You can manipulate the various lattice parameters, alpha, beta, gamma value, ABC value, primitive cells, conventional cells, even armchair, zigzag type of graphene nano ribbons, nanotubes, and grain boundary. So advanced tools are there for building the structure along with the user-friendly interface. So here you can define, set up the parameter, DFT parameter, DFPT parameter, electron temperature, cutoff energy, exchange correlation, K-point sampling, iteration control, and spin tonic calculation. So also you can calculate the various property, electronics property, structural property, optical property, thermal property, magnetic property, electronics and thermal transport property, electron-phonon coupling. Now, the bigger application of this software for molecular structure simulation, molecular material-based device structure simulation, surface simulation, 2D material-based device structure simulation, hexagonal, tetragonal, tri-black phosphorus material-based simulation, interface between different geometry and different symmetry, and some carbon-based material simulation, different alloy, different doping, structural defect, point defect, line defect, and other type of simulation you can do. So, as I have already said, RESCU and RESCU Plus, they designed to address the large scale atomistic simulation of material and large scale atomistic simulation of materials. So that are increasingly so becoming important because atomistic simulation are the state of art method that has the accuracy and transferability of the simulation from various small scale systems to large scale systems, and they are not necessarily replacing non-quantum mechanical approach that can also be used to simulate material that over large scale, but they are important part of the simulation tools, and they can be actually to complement simulation of material with non-quantum mechanical method large scale. So they are increasingly becoming important at every large scale simulation. So here in term of accuracy, RESCU also cover all the steps in the accuracy adder of the atomistic simulation. So one of the main advantage of this RESCU is that it cover all the accuracy level of electrons in the material. You can simulate LDA, GGA, meta GGA, and Hartree-Fock exchange, collinear spin, non-collinear spin, spin orbital interaction. So all feature will be there. You can simulate their structure. So in terms of analysis tool, we have a very complete list of analysis tool. For example, here you can see this is the band structure and density of state calculation from this RESCU software. So one of the main advantages is that they cover a few main basic sets that are used in material simulation. So for example, band structure, this is the band structure for the numeric, atomic orbital, and real space basis. And this is very important part of the RESCU, which gives the user to ability to benchmark their simulation. And in terms of computational and numerical details, one of the main advantages of RESCU that it has gathered all the different approach to atomistic material simulation under the umbrella of one software. So we have a very powerful DFPT toolbox, and also this is one of the main strength of this RESCU. So basically, by using this DFPT toolbox, we are able to calculate the variety of material property that are based on response of material, external perturbation theory, like dielectric constant, vibrational property, phonons, optical property, interaction of electrons with the photons, which is representative of this temperature in the material. So with the DFPT toolbox, we are able to cover and simulate many of those properties. So currently with the DFPT toolbox, response for the electric and atomistic simulation, displacement, perturbation theory, and this is important because material property and Raman property tools such as Raman spectroscopy, they are actually based in the kind of material response like XML probes, and we are able to cover that simulation and perform those kind of simulation. One of the main advantage of our DFPT toolbox is that this is the state of solver while BI, BICG and CFSI Chebyshev filtering. So we here you can see this is the some example of DFPT calculation, and here you can see example of the dielectric constant of the several material which calculated with the RESCU. This is an accuracy benchmark. So we can see that our result matches perfectly with the experimental and also with the other numerical codes and methods. And also we have a performance benchmark of the RESCU. So you can see that easily RESCU easily a system up to more than 400 atoms, and this is the tough computational problems for all the other computational atomistic code. But with our state of solver, you can easily calculate up to 20,000 atoms. So here you can see this is the another example of DFPT toolbox. And again, this is the phonon band structure and density of state of diamond. We see that they calculate the result perfectly, match the experimental measurement. And also on the right, we see that we can easily calculate the density of state for diamond of the supercell containing 260 atoms. So basically, you can perform this kind of calculation for every atoms that you have in your system. So here we see another example of DFPT toolbox, and again this is the optical property. Yes, this is the optical property of this hexagonal aluminum nitride, and we see that atomistic simulation can capture all the main features of this optical spectra of this hexagonal aluminum nitride. This is the dielectric permittivity, and this is the refractive index. And here we see that infrared intensity of the perovskite material. We see that this simulation result perfectly reproduce the infrared peaks of these materials. And by using our state-of-art DFPT solver, we see that 64 core at we can calculate the full infrared intensity of this material in less than half an hour. So as compared to the, here you can see this is the comparison with the quantum espresso. So this is a classic example of this type of information that one can achieve from this atomistic simulation of the material. Here we can see that this is the Raman spectra of a silicon nanowire. So these nanowire are constructed from the different phase of the silicon, that is 9R and 3C. So if you individually study this focus, then you will see that Raman peak at frequency which are different than the Raman peak from this frequency of this silicon nanowires. And this is for an example of the prediction of the simulation. So here we can see that this is the nanowire. Actually, the 9R peaks different peak efficiency is higher than that the 3C. So RESCU is basically a state-of-art general-purpose first principle Kohn-Sham DFT package based on advanced numerical, mathematical, and parallel implementation that can predict material property on a small-scale computers. So it can include common electronic structure analysis tools and implement a perturbation theories which allow computing all sort of response like polarization, phonon band structure, optical property. And this software is written in MATLAB NC, and you can simulate the material up to 20,000 atoms. And this is the DFPT implementations where you can dielectric tensor, dynamical matrix, and optical property, dielectrical property, permittivity, refractive index, tensor for this Raman tools, spectrum intensities, and advanced functional like a DFPT plus U, and all common analysis like density of state, phonon density of state, local density of state, polarized local density of state, band structure, band unfolding, charge analysis, and all nonlinear optical susceptibility, spintonics, collinear, nonlinear, spin orbit coupling, phonon tools, large scale CFSI. So this is all about this rescue. And I have already told you they have also launched the RESCU Plus for the large scale DFPT. So in comparison with the RESCU, which is written in MATLAB NC, and this RESCU Plus is written in Python and Fortran. So RESCU Plus is most powerful code for the both like plane waves and atomic orbitals, and it can simulate up to 100,000 plus atoms. And RESCU Plus uses a user-friendly Python interface, so it is really convenient to build the workflow. And it comes with the additional for a large structure relaxation, molecular dynamics, and NEV calculation. So this is my contact details. So for any help, so you can directly contact or you can send us mail so that we can try to help you. So thank you for listening this presentation. I would switch on this demonstration part. So I would like to open my device studio. So here you can see this is the device studio folder. and the software is located in the bin folder. Here you can see this is the device studio application file. So you can double click on this file, and then this interface will open. Like this is creating the new project, and you can open your existing project. So I would like to start from this scratch. So you can click on this create a new project. Then you can click on this OK. And here you can enter the name of your project, and then you can click on this save option. So in the first session, I will show you what the simulation you can do from this rescue. And in the second session, you can do the hands-on. So on the left side, you can see this is the project explorer where the input and output file will be shown. And this is the property explorer where the property of our whole structure are either you can individual item you can see. And this is the job manager. And in the menu bar, you can see this is the file option. And in the file you can see this is for creating the new project. You can open the existing project, you can save your project, you can design your new device structure, crystal structure, molecule structure, and this is the import option. So this software have two options to import the material. Either you can import the material from local database that exists inside this software, or you can import the material from online database. So you can select this import local, and here you will find the material database like 0D material, 1D material, 2D material, 3D material, and some organic material is there. In 0D material, you can see some molecules, amorphous and crystalline is there. This is the amorphous, and this is the crystalline. And this is the 1D material where nanotubes in different combination of crawl vectors is there. And this is the 2D material where novelty materials, this is the novelty, arsenic, bismuth, black phosphorus, and this is the graphene. This is the 3D material where you can see conductor, insulator, layer material, magnetic material, metal oxide, novelty material, semiconductor is there. And this is the conductor, pure metals. And this is the insulator. This is the layer material. This is the magnetic material. This is the metal oxide. This is the novelty material, some perovskite, topological insulator. This is the perovskite. And this is the topological insulator. And this is the semiconductor. And here you can see organic material is also there. So this is the organic, some crystal and molecule is there. So the conclusion is all that this is the material database that exists inside this software. And if you select this import online option, so then this interface will open. And here you can enter the chemical formula. Like this is the MOS2. And then you can search this. And this is the MOS2 with different combination. And here you can see different space group is also there. So as per unit, you can select and then you can click on this add option. And in the new option, you can see this is the crystal option. If you want to design a crystal, so either simple structure, complex structure, you can also design. Here you can see various space group are there. 1p1, 2p1, 3p2, and this is the Brebes lattice triclinic. So according to the space group, the Brebes lattice will automatically selected. And also you can change the ABC value, alpha, beta, gamma value. You can add the elements through this plus option, and you can show their primitive cells, conventional cells, and then you can click on this preview option. Like if you want to make a gold crystal structure, so simply you can select their space group. This is the space group for this gold atom, and here you can see face center cubic structure. This is the Brebes lattice. And also you can change the ABC value, and then here you can select the atoms. Here you can see default carbon atom is selected. But if you want to change this carbon with another atom, so you can double click on this carbon, then periodic table will open. And from periodic table, you can select any atoms, like this is the gold. And then you can click on this OK. And here you can see in the primitive style, primitive cells, conventional cells. So this is the primitive. Then you can click on this preview option. So this is the primitive cells of this gold atoms. And if you want to show the conventional, so you can select this conventional cells, and then you can click on this preview option. And this is the conventional cell of this gold atoms. So this is the primitive, and then you can click on this build option. So either simple structure, complex structure, any structure you can build from this crystal builder. Then you can click on this build option. And in the menu bar, you can see this is the build option. And in the build option, you can see multiple options are there. This is the molecule 3D builder. This is the molecule 2D builder. And this is the decomposition. This is the device maker. And here you can convert your device. And this is the bending of device structure, interface builder, fill junction with the atoms. And this is the cat to atomic crystal builder. So if you want to design the molecule, so this is the molecule 3D builder. And if you want to add the element, so here you can select this plus icon, and then periodic table will open. So from periodic table, you can select any atoms. Like this is the oxygen, and this is the different fragmentation of this oxygen. So if you want to select this oxygen, then you can press here. So this is the oxygen, and this is the hydrogen. So this is the S2 molecule. And if you want to add more hydrogen, so here you can see this is the add hydrogen. And here you can see this is the modify bond. So you can select this one, and you can select two atoms. And here you can see this is the single bond, this is the double bond, this is the triple bond, and this is the resonance bond, and this is the half bond. So this is the double bond, this is the triple bond, and this is the resonance bond, and this is the half bond. So as per your need, you can select. And also if you want to fix your atoms, like this is the atom 1 and atom 2. So this atom will be fixed. And then you can click on this OK. And if you want to modify their angle, so here you can see this is the modify angle option. So you can select this one, and you can select three atoms. Through this option, you can modify their angle, or you can enter the angle. Like this is the 90, and then you can enter. And if you want to fix first atom, so you can fix first, and atom 2 and atom 3 will be rotated. Like here you can see atom 1 is fixed, and atom 2 and 3 is rotation. And if you want to fix atom 2, then atom 3 will be rotated. And this is the dihedral angle. So you can select 4 atoms. And you can modify their angle. And if you want to add more atoms, so you can select this plus icon. And from periodic table, you can select any atoms. Like this is the carbon. And this is the fragmentation I want to select. And then you can press here. So any complex structure, simple structure you can do. And then you can click on this supply data. And in the toolbar, you can see the force field calculation, UFF, GFF, chemicals. And if you want to create a molecule 2D structure, so you can select this molecule 2D. And on the left side, you can see various fragmentation are there. Like this is the aryl group and this is the cyclohexyl. This is the cyclohexyl group. And if you want to draw the single bond, so here you can see this is the single bond. So any structure you can create like that. And if you want to change this S3 with hydrogen atoms, so you can click on this S3 and this is the S3 atoms. So I hope my screen is visible to all of you. So again, I can repeat. So if you want to simulate this structure, so you can click on this simulator, go to the RESCU, and this is the SCF calculation, relaxation, DFPT, and this is the analysis parameter. So you can select as per your need. So I would like to select this self-consistent field calculation. And this is the SCF parameter where you can see some basic settings, simmering sigma, resolution, and this is the method for this SCF. Real space, linear combination of atomic orbitals, and this is the exchange correlation, LDA, GGA, and this is the von Neumann, and this is the imperative band, and this is the K-point sampling. This is the iteration control where you can see this is the tolerance, charge density, total energy, and this is the maximum SCF state, mixed method, Poulet, quadrant, linear and quadratic is there. And this is the mixed variable, density matrix, potential, and this is the basic settings like arrangement by element, and this is the Howard terms. Like some SPDF combination is there. And this is the spintronics application, like collinear spin, general spin. So if you select this collinear spin, so this is the collinear spin, and this is the magmum. And this is the general spin, where you can see this is the spin orbital interaction. So you can select like this is the collinear spin. So you can select any value and then you can click on this generate file. So once you click on the generate file in the project window, you can see the scf.input file and atom.xyz file has been generated. So you can select this scf.input file, right click, select this open with, and this is the script for this MOS2 structure. Here you can see what parameter we have defined. And this is the atom.xyz file. So you can select this open with, and this is the atom and their Cartesian coordinate point. So first you need to run this scf.input file, right click, select this run option. And if you want to run this Java on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core. You can define up to 128 core. Then you can click on this run option to run this job. In the bottom of the page, you can see this is the job manager where the scf.input file is in the running condition. So in the meantime, if you want to analyze their parameter, so you can click on this simulator, select this RESCU and go to the analysis. And this is the density of state, band structure, molecule population, and this is the potential. Like this is the density of state. And this is the K-point sampling, N1, N2, N3. And this is the energy range, number of energy point, and this is the K-point sampling. And this is the simmering sigma. And if you want to calculate the projected density of state, local density of state, so simply you can select. This is the projected. And if you want to show with the atom wise, so you can select the atoms. and then you can search the atoms like and if you want to calculate this local density of state, so you can select this one and then you can define their energy, and then you can click on this generate file. So this is the local density of state.input file. So similarly you can run this local density of state, then you can run this option. And if you want to calculate more property, so again you can select this simulator, select this RESCU, go to the analysis, and this is the band structure, this is the potential, this is the symmetry K point, and this is the Brillouin zone path. Then you can click on and this is the potential, and then you can click on this generate file. So similarly you can run all the analysis input file, and once their calculation will finish, their output will be generated. And here you can see the rescue log.output file has been generated, so you can click on this open with. And here you can see this is the calculation method, stepwise step. And here you can see this is the total time taken by this, 3 minutes 24 seconds. So here you can see density of state calculation has been finished, and for the output you can see, go to the simulator, select this rescue and go to the analysis plot, and here you can relocate your project. Here you can see this is my project, then you can select this folder, and this is the MOS2 folder, and this is the rescue crystal folder, and this is the result folder. Here you can see this is the density of state, and this is the local density of state, and this is the potential. So you can select this local density of state, then you can click on this open. And this is the 3D view of this local density of state. If you want to show the 2D, so this is the 2D along x-axis, y-axis, z-axis, and this is the spin up. If you want to show the spin down, so this is the spin down, and this is the planar display, stereoscopic display, and this is the 1D view. This is for the spin down, and this is the spin up. And if you want to export your raw data, so here you can see this is the export option. So you can select this option, and here you can select the format like JPG, BMP, PDF, text format. So any format you can select, and then you can click on this save option. Like this is the JPG, and then you can click on this save option so that you can easily export your raw data in any format. So here you can see this is the local density of state that I have exported. And this software is also integrated in the MATLAB. So if you have MATLAB, so here you can see this is my MATLAB. And from this browse option, you can locate your project in the MATLAB. This is my project. Then you can click on this select folder. And here you can see this is the MOS4 and their output file. And this is the result folder. Here you can see this is the density of state, and this is the density of state.mat file. So you can select, double click on this file, and then here you can type the DFPT. One second. In the right side, you can see this is the atom, and you can double click on this data, and this is the output for this local density of state. This is the XYZ position, and this is the magma. And here you can see this is the energy. This is the Fermi energy, and this is the entropy. Here you can see the band structure is running, and this is the step. And in the meantime, if you want to calculate the phonon band structure, phonon density of state for the diamond, so you can draw the diamond. So you can select this file option, select this new option, go to the crystal option, and first you can select their space group. So I would like to select their space group 195. This is the 195 simple cubic structure, and then you can change their ABC value as per your need. And here you can select this carbon atoms. This is the carbon, and also you can change their fractional coordinate point. So if you want to add more number of carbons, so you can select this plus icon, and simply you can select the fractional coordinate point. This is the carbon. So you can select the carbon atoms, and you can define their fractional coordinate point, and then you can click on this preview. So this is the gold crystal structure, and this is the primitive cells. If you want to show the conventional, so you can select this conventional, and then you can click on this preview. So I would like to select this primitive cells preview, and then I would like to click on this build option. So here you can see all the calculation has been finished. So for the output, again you can select this simulator, go to the RESCU, select this analysis plot, and here you can see this is the band structure, and this is the potential. So I would like to select this band structure, then you can click on this open. This is the band structure. Here you can see this is the conduction band, and this is the valence band, and this is the Fermi energy. And this is for the spin up. If you want to show the spin down, so this is the spin down. And if you want to show the both spin up and spin down, So this is the band structure for this MOS2 for the spin up and spin down calculation. And if you want to show the potential output, so again you can select this simulator, select this RESCU, go to the analysis plot, and you can select this potential. So this is the 3D view of this potential, and this is the 2D view along x-axis, y-axis, z-axis, and this is for the spin up, spin down. And this is the 1D view along xy plane, yz plane, xz plane. So any plane you can select and you can show their data. And then if you want to calculate this diamond crystal structure, so again you can select this simulator, select this RESCU, and this is the further relaxation if you want to optimize this structure, or you can select this DFPT density function perturbation theory. So in the task, you can see this is the phonon band structure calculation, and this is the phonon density of state, this is the phonon density of state and phonon band structure, and this is the optical property, and this is the Raman property. So you can select any parameter, like this is the phonon band structure and phonon density of state, and you can define their simmering sigma, resolution, SCF method, this is the real space, and you can change their exchange correlation, LDA, GGA, and you can change their K point sampling, this is the iteration control, and this is the SCF parameter, and this is the DFPT parameter. In the DFPT method, you can see this is the Sternheimer, and this is the Chebyshev filtering. This is the basic settings, and this is the spintonics application, and this is the phonon band structure parameter. Here you can see this is the symmetry Q point, and this is the line zone path, and this is the number of Q point, and this is the phonon density of state parameter Q point sampling. So you can define their parameter as per your need, and then you can click on this generate file. So once you click on generate file, in the project window you can see the SCF.input file, the dielectric.input file, phonon.input file, phonon band structure.input file, phonon density of state.input file has been generated, and this is the atom.xyz file. So you can select this SCF.input file, right click, select this open with, and this is the script for this diamond crystal structure. And here you can see what parameter we have defined. And this is the dielectric.input file. So you can select this folder and you can click on this open with. And this is the phonon input file. So first you need to run the scf.input file. Right click, select this run option. Here you can define the number of parallel code, then you can select this run option to run this job. And then you can select this dielectric.input file. Right click, select this run option to run this job. So similarly, you can run all the input, like this is the phonon input, and this is the phonon band structure input file. This is the phonon density of state input file. And this is the atom.xyz file. So this is, you can click on this open with, and this is the carbon atoms and their Cartesian coordinate point. Here you can see this is the property explorer. Total number of atom is 8, and you want to show this individual atom, so you can select any atoms, and here you can see this is the carbon and their XYZ position. So in the job manager, you can see I have run all the calculation in the queue condition. Like when this phonon input file has been calculated, then this phonon band structure input file will start automatically. Here you can see the scf.input file has been finished, dielectric is also finished, and phonon is running. So you can wait till the calculation finished. Once their calculation finished, their output file will be generated. And this is the output folder. And you can see this is the calculation method and their step. In the meantime, you can select this video option. And if you want to import silicon atoms, so you can select this file option, go to the import option, select this import local. And here you can see this is the 3D material. Select this semiconductor. And here you can select this silicon. And then you can click on this open. And if you want to show their face center cubic structure, body center cubic structure of this silicon, so you can select this build option. And here you can see this is the redefined crystal. And you can redefine by expressing the new cell vector UVW as a linear combination of ABC. And this is the face center cubic structure, and this is the body center cubic structure. So I would like to select this face center cubic structure. Then you can select this preview option. And this is the face center cubic structure of this silicon atoms. And if you want to show the body center cubic structure, so this is the body center. You can select this preview option. And this is the body center cubic structure of this silicon atoms. So I would like to select this face center. You can select this preview option. Then you can click on this build option. And in the build, as you can see, this is the surface slab and this is the symmetry. You can standardize your cell. This is the graphene nano ribbons, nanotubes. This is the grain boundary, nanotubes, nanowire. And this is the disordered graphene-like structure, disordered zinc blend-like structure. This is the icosahedron and this is the cuboctahedron. So if you want to create a surface slab, so you can select this surface slab. So for this surface slab, you can select this surface slab. And here you can see this is the clean plate, like Miller indices SKL value 100, 111, 101. So whatever combination you want, you can select. And here you can see this is the silicon atoms and their fractional coordinate point P1, P2, P3. And this is the surface primitive cell vector UV, and this is the vacuum. And you want to add this slab, so here you can select this slab option, and you can increase their thickness. You can add the vacuum, like this is the thickness. And if you want to include the vacuum, so here you can see the thickness and vacuum has been added. And then simply you can click on this build option. In the job manager, you can see all the input calculation has been finished and their output has been generated. So you can select this simulator, select this rescue, go to the analysis plot, and this and here you can select this result folder. One second. Here you can select this crystal folder, and this is the rescue DFPT, and this is the result folder. Like here you can see this is the band structure, and this is the density of state. And this is the dielectric output file, and this is the phonon output file. Once their output has been generated, you can open the MATLAB. And on the left side, you can see this is the crystal folder and their output folder. And this is the result folder. And here you can see the phonon.mat file. And this is the phonon structure.mat file. And this is the density of state.mat file. So simply you can select any file. So here you can see this is the phonon structure. And simply you can type the DFPT command and then you can press the enter. And here you can see this is the output. And for the plotting the graph, so either you can click on this new script and you can write their script for plotting, or either you can select this simulator, select this input file, phonon structure, and you can open this file. And here you can write this command. You can write RESCU. And you can copy this path. You can copy this mat file path. Control C. And here you can press. You can save this file. So you can save this file. And then again you can need to run this file. So similarly for this phonon density of state, you can select this file, select this open with, and here you can write this command. This is for the density of state, and then you can save this file. And again you can run this phonon density of state, so that their data, output data has been plotted in the MATLAB. So you can open this MATLAB. Here you can see the band structure has been finished and density of state is also finished. So you can open the MATLAB, and here you can see the data has been plotted. So this is the phonon band structure and this is the phonon density of state. So you can select this phonon band structure, and this is the phonon band structure for this diamond crystal structure. So similarly you can select this density of state, and this is the phonon density of state for this diamond crystal structure. So either you can write the script or you can change the input folder. In the input folder, you can write this command, then you can save this option, and again you can run this program. Again you can run this input file, and then their output will be plotted in the MATLAB. So again you can select this build option. And if you want to design graphene nano ribbons, nanotubes, grain boundary, so if you design this graphene nano ribbons, so you can select. And here you can see this is the carbon atom, site A, site B, and this is the bond length, and this, if you want to passivate with this hydrogen atoms, and then you can check copy this checkbox, and this is the crawl vector and name value, and then you can click on this preview option. So this is the 2x2 graphene nano ribbons. So this is the armchair. If you want to design a zigzag, so you can select m is equal to 0, then you can click on this preview option. So this is the zigzag. And if you want to design a boron nitride based nano ribbons, so simply you can change this carbon with boron. This is the boron, and on the side B you can select this nitrogen, and also you can modify their bond length. Then you can click on this preview option. So this is the 4x4 boron based nano ribbons, and then you can click on this build option. So this boron nitride nano ribbons is quite thin in the direction of C. So if you want to increase the length, then you can click on this build option, select this redefine crystal, and here you can redefine in any direction like A, B, C. So I would like to increase in the transport direction, and then you can click on this preview. So here you can see the length has been increased in the transport direction, that is C. And then simply you can select this build option. So this is the single layer boron nitride. If you want to design a multi-layer boron nitride, so simply you can select all the atoms, go to the mirror option, and here you can see this is the normal vector XYZ, and this is the distance. So I would like to select this XY normal vector, and then you can define the distance. Then you can copy this checkbox, and then you can click on this apply. So here you can see this is the mirror in the XY direction. And simply if you want to move this atom in the unit cell, so you can select the atoms, go to the move option, and in the move option you can see multiple options are there, like translation along XYZ position, ABC cell vector, and this is the along screen view. So I would like to select this along screen view, and you can move these atoms either left side, right side. And then you can click on this recalculate linker bond. So here you can see this is the double layer boron nitride nano ribbons. So either single layer, mono layer, bi-layer, tri-layer. So any layer structure you can simply create, and you can do their simulation. And if you design a nanotubes, so here you can see this is the graphene nanotube. So again you can select the crawl vector, and then you can click on this preview option. So this is the 2x2 graphene nanotubes. If you want to increase this crawl vector, and then you can click on this build option. So again you can select this build option, go to the redefine crystal, and you can redefine in the transport direction, and then you can click on this preview. And again you can select this build option. So this is the 4x4 nanotubes. And in the build option you can see this grain boundary. And here you can see the coincidence site lattice, and this is the value of sigma 3, 5, 7, and this is the axis. This is the value of theta, and this is the cos theta. So you can then click on this preview option. And if you want to change the value of this sigma, then you can select this preview option. So whatever combination of sigma, axis, and theta, cos theta you want, so simply you can select, and then you can click on this preview option. And for building the structure, you can select this build option. And here you can see this is the nanotube. If you want to make a silicon nanotubes, so here you can find the crawl vector and an m value, and then you can on this preview option. So this is the 2x2 silicon nanotubes. And this is the 5x5 silicon nanotube. And then you can click on this build option. Again, you can select this nanowire if you want to make a nanowire of this silicon. So here you can see this is the wire direction 100, 110, 111, and this is the cluster parameter. This is the cluster radius, and this is the surface energy for the 100, 110, and this is the 111. Then you can select this preview option. So this is the silicon nanowire for this 100 wire direction. If you want to show with the 110, so you can select, and then you can click on this preview option. So any wire direction you can select, you can preview, and then you can click on this build option. And here you can see this is the disorder graphene-like structure. And this is the side shell, side A, side B, and this is the bond length, and this is the crawl vector, supershell. Then you can click on the build option. And if you want to calculate the Raman property of any crystal structure, molecular structure, so simply I would like to select this aluminum nitride from this import option. And then you can click on this search option. So here you can see this is the aluminum nitride with the different combination, and this is the various space group. So I would like to select this is aluminum nitride, and then you can click on this add option. Similarly, you can select this simulator, select this RESCU, go to the DFPT, and in the task you can select this optical or Raman, any parameter you can select. So I would like to select this Raman property, and then you can define the signaling sigma, resolution, DFT, SCF method. This is the real space, and this is the exchange correlation, LDA, GGA, and this is the K-point sampling. This is the iteration control, SCF parameter, and this is the DFPT parameters. This is the basic setting. This is the aluminum, and this is the nitro, and this is the double zeta polarized. And this is the spintronics application, and this is the Raman and their parameter like damping factor, Q-point Cartesian, and this is the income photon polarization, and this is the outcome photon polarization, and this is the income photon wavelength, and this is the temperature. Here you can see this is the wavelength is in the angstrom, and temperature is in the Kelvin. So as per need, you can select the parameter, and then you can click on this generate file. So again you can see the SCF.input file, dielectric.input file, phonon.input file, Raman.input file, atom.xp file has been generated. So first you need to run this SCF.input file. Right click, select this run option to run this job. In the same way, you can run all the input file. And this is the atom.xyz file. This is the aluminum and this is the nitrogen and their Cartesian coordinate point. Here you can see the sf.input file has been finished and the dielectric.input file is in the running condition. So you wait till the calculation finish. Once their calculation finished, their output.mat file will be generated. And in the build option, you can see this is the disorder zinc blend like structure. This is the site A carbon atom and site B is also carbon atoms, and this is the bond length, and then you can click on this preview. And if you want to change this carbon with another atoms like zinc, then you can select this zinc. And here if you want to change with oxygen, and then you can select this preview option. So this is the ZNO zinc blend like structure, and then you can click on this build option. You can see dielectric input file is also finished, phonon is also finished, and Raman is in the running condition. And if you want to calculate the optical property of this silicon, here you can see all the calculation has been finished and their .mat file will be generated. So you can open the MATLAB. And here you can see this is the aluminum nitride. Output, this is the RESCU folder. And this is the result folder. Here you can see .mat file has been generated, but their graph is not plotted. So you can select this Raman.mat file, and here you can type the command DFPT. Then you can press the enter, and here you can see this is the Raman output. Again you can type the Raman and then press the enter, and here you can see this is the susceptibility, and this is the tensor, and this is the dipole ratio, and this is the spectrum. So if you want to plot the Raman spectrum, so either you from this new script you can write there is, or you can go to this device studio folder. You can select this Raman.input file, right click, select this open with, and here you can write the command, and you can copy this. You can copy this path, and then you can click on this save option. This is for the Raman phonon. So for the Raman, you can type here Raman, and then you can save this input file. Again, you need to run this Raman.input file. And once this calculation finished, their output graph will be plotted in the MATLAB. So here you can see the graph has been plotted in the MATLAB. So you can open the MATLAB, and here you can see this is the graph. So this is the polarized graph of this aluminum nitride. Here you can see this is the Raman intensity, and this is the Raman shift. And this is the average polarized Raman graph. This is the Raman intensity, and this is the Raman shift. Here you can see this is the peak frequency. If you want to show the data, here you can see this is the data, and this is the minimum peak value. This is the minimum peak value. This is the... And if you want to calculate the optical property of this silicon, so again you can select this simulator, go to the RESCU, select this DFPT, and in the task you can select this optical property calculation, and also you can define their parameter. And this is the optical parameter, this is the damping factor, and this is the E field direction. And then you can click on this generate file. Similarly, you can run this scf.input file first. Again, you can run this dielectric.input file. This is the phonon.input file, and this is the optical.input file. Here you can see the sf.input file calculation has been finished, and the dielectric.input file is in the running condition. In the job manager, you can see all the calculation has been finished, and their output will be generated. So you can open the MATLAB, and this is the silicon folder. And this is the silicon folder, and this is the RESCU DFPT folder. You can open this result folder. And here you can see this is the phonon.mat file, and this is the SI optic.mat file. So you can select this file, and here you can type the command DFPT. Then you can press the enter, and simply again you can write the command optic, and then you can press the enter. Here you can see this is the infrared frequencies, and this is the IR intensities. This is the dielectric frequency, and this is the dielectric function. This is the energy loss. So if you want to plot the graph, here you can see the data. The graph has not been plotted. So for plotting the graph, you can open the simulator. Again, you can select this optical.input file. Right click, select this open with. Again, here you can type the command. You can copy this path. Control C. And here you can paste it. Then you can save this input file. Again, you need to run this optical.input file. And you can wait till the calculation finished. Here you can see the calculation has been finished. And you can open the MATLAB. This is the optic. You can copy the optic.mat file and then you can save this file. And then you can run this optical.input file. So we can open the MATLAB. And here you can see this is the dielectric function, this is the IR intensities, and this is the energy loss, and this is the refractive index. So you can select this folder, double click, and this is the dielectric permittivity, and this is the real axis, and this is the imaginary axis. Because I have taken the default parameter. So once you define their parameter, then their output will be plotted accurately. And this is the IR intensities. And this is the energy loss. This is the photon energy loss. And this is the refractive index. This is for the real part and this is for the imaginary part. And if you want to make a semiconductor heterojunction, so either you can import the semiconductor from the import option, import local or import online. So I would like to select this import local option. This is the 3D and this is the semiconductor. So I would like to select this aluminum arsenide. And again, I would like to select gallium arsenide. And this is the gallium arsenide. So you can select this gallium arsenide, go to the build option. If you want to make a supercell, you can select this build option, go to the redefine crystal, and you can redefine in any direction A, B, C. So I would like to redefine 2 times in the direction of A and 2 times in the direction of B and 4 times in the direction of C. Then you can click on this preview option. And here you can see this is the supercell of this gallium arsenide. Then you can click on this build option. Again, you can select this aluminum arsenide. So if you want to make a supercell of this, so again you can select this field option, select this redefine crystal. Again you can redefine the crystal 2 times in the direction of A, 2 times in the direction of B, and 4 times in the direction of C. Then you can preview, and this is the supercell of this aluminum arsenide. Then you can click on this field option. And to make a heterojunction, you can select this field option, go to the interface builder, and in the structure A, structure B, you can look at this project. So here you can see this is the aluminum arsenide, gallium arsenide, and this is the aluminum arsenide. So I would like to select this gallium arsenide, and in the structure B, I would like to select this aluminum arsenide. Then you can select this match option, and here you can see this is the number of atom versus mean absolute strain graph. You can then click on this preview option. So this is the semiconductor heterojunction of this gallium arsenide and aluminum arsenide. And here you can see this is the strain first surface, and this is the strain second surface. You can match, you can preview, and this is the strain both surface. Again you can select this match option, you can select this preview option. And if you want to decrease some atoms, so you can select this graph, and then you can click on this preview option. So from this graph, either you can decrease the atoms or either you can increase the atom. Here you can see total number of atom is 288, and this is the angle, this is the rotation, this is the mismatching, and this is the area strain. And then you can click on this build option. So this is the semiconductor heterostructure. If you want to make a Schottky junction of this aluminum arsenide or any aluminum, so first I would like to import the aluminum. And here you can see this is the aluminum, and this is the gallium arsenide. So you can select this aluminum. Again, you can make a supercell. So you can select this build option, go to the redefine crystal, and 2 times in the direction of A, 2 times in the direction of B, and 6 times in the direction of C. Then you can click on this preview option, and then you can click on this build option. So similarly, again, you can select build option, interface builder, and in the aluminum arsenide, you can define the aluminum. Then you can mesh, then you can click on this preview. So this is the Schottky junction of this gallium arsenide and aluminum. And if you want to make a 2D heterostructure, so this is the semiconductor heterostructure. If you want to make a 2D, so first you need to import the 2D materials. This is the 2D. This is the graphene. Again, I would like to import boron nitride. This is the 2D material. And this is the boron nitride. So simply you can select this boron nitride, select this field option, go to the redefine crystal, and I would like to redefine 30 times in the direction of A, 30 times in the direction of B. Then you can click on this preview option.
Excuse me, sir.
Yes, ma'am.
Sir, are you randomly selecting these 36 or 2?
No, ma'am. As per, I am taking the default parameter. You can select as per your need.
Okay, sir. Thank you.
So as per your need, you can define like in the direction of U, V, W, A, B, C, any parameter you can select, and then you can click on this preview option. Again, you can select this graphene. Similarly, you can select this build option. Go to the redefine crystal. Again, I would like to redefine 30 times in the direction of A, 30 times in the direction of B. Then you can click on this preview option. And then you can click on this build option. And if you want to increase some vacuum from this graphene nano ribbons, so you can select this convert to crystal option. And here you can see this is the vacuum energy A, B, C. So as per your need, you can define, and then you can click on this build option. Here you can see the vacuum energy has been added, and then you can click on this build option. Simply, if you want to make a 2D heterostructure, so you can select this boron nitride, copy this all atoms, Control C, and Control V inside this unit cell. Again, you can select this center option to make it centrally fit. So this is the boron nitride and graphene based 2D heterostructure. And here you can see this is the 3D viewer. You can show their XY view, XZ view, YZ view, YX view, and this is the ZX view. This is the XZ view. And if you want to twist this graphene sheet, so you can select this graphene sheet, go to the rotation option. And in the rotation, you can see multiple options are there, like along XYZ axis, ABC vector, and this is the screen vector. So I would like to select this screen vector. You can define the angle. So either left side, right, x-axis, y-axis, or z-axis, you can define. So here you can see I have to state this graphene sheet. And you can do their analysis like band structure, density of state. And if you want to create a defect in this structure, so simply you can select the atoms and you can delete. So here you can see the defect has been created. And in the toolbar, you can see this is the convert to molecule option, and this is the distance measurement. If you want to measure the distance, so you can select this option, select any two atoms, and here you can see this is the distance 2.352 angstrom. And here you can see this is the angle measurement. So you can select any three atoms, and this is the angle. And this is the dihedral angle measurement. So you can select any four atoms, and this is the angle for this dihedral angle. And here you can see this is the vector measurement. So you can select any two atoms, and this is the vector value for this two atoms. And in the file option, you can see this is the import option, and this software support this file format .szw, .xyz, CFI, CIF, XSD, postcard. So this file format you can directly import into the device studio. And suppose if you have another format, so you can click on this build option, and here you can see the convert file option is there. So from this you can locate a project like where your file is located. Like here you can see this is the .py file. So you can select this file, select this open option, and here you can convert this file into the .szw.xyz file format. So any format you can select, and then you can click on this option. Here you can see the file has been converted in the .szw file, and this file you can directly import. Here you can see the file has been converted. You can select this file, and then you can click on this open. So I have show you the maximum property of this software. If you have any specific query, so kindly unmute your mic so that we can try to resolve. So kindly you can unmute your mic and ask me the query, whatever query you have, and then I will try to solve you.
Hello, sir.
Yes, ma'am.
What are the minimum requirements to run this software? System requirements.
Sir, your voice is not good. Sir, can you repeat again?
What are the minimum system requirements to run this software? Hello.
Yes, ma'am. Can you repeat once again?
What are the minimum system requirements to run this software smoothly?
Ma'am, as much as your system is good, you will get the faster speed. But generally, we recommend a 16 GB RAM and 16 core processor.
Can you please repeat again?
Yes.
I couldn't hear your voice. Can you please repeat it again?
Ma'am, as much as your system is good, you will get the faster speed. But generally, we recommend a 16 GB RAM and 16 core processor so that you can do the simulation.
Okay. Thank you.
And in my software, you can see, and this is the 12 core processor.
Hello, sir.
Yes, ma'am.
What can you tell me about if I want to run my calculations through quantum espresso or WASP? Which one is better among these three?
Ma'am, as you know, in the Quantum Espresso WASP, the user interface is not there. And this software support the user interface. This is the graphical user interface of this RESCU software. So that you can model the structure, you can do their simulation in the device studio. And for the background, you can select this RESCU. But in WASP and Quantum Espresso, the user interface is not there. So you can save your time in the device RESCU software. And also RESCU software have more benefit over the Quantum Espresso, WASP. So as you saw my presentation, you can see. Here you can see this is the calculation with the Quantum Espresso, and this calculation is with the RESCU software. Here you can see the total time taken is less than half an hour, and this from this Quantum Espresso, here you can
Thank
see
you, sir.
1.5 hour. Yes.
Thank you, sir.
In the RESCU software, you can see this is the relaxation. So optimization is also possible in this RESCU software. And here you can see this is the relaxation, and this is the method. Quasi-Newton, steepest, conjugate gradient. So any method you can select and you can optimize your structure. Here you can see this is the relax.input file. So anyone has more queries? So kindly unmute your mic and ask me so that I can try to resolve. So from my side, thank you to all of you for joining this first session. So we will meet you at 2 p.m. for this hand.